Welcome, everybody. In this episode, a look at the role that hydrogen has to play in a future that's powered by renewable energy. More specifically, we're going to dive into some of the research that's helping to tackle the challenges and helping to realize the potential of using hydrogen as a way to store power that's generated from renewable sources like wind and solar. And if you stick around long enough in the interview, you'll hear of a way that some of this research around hydrogen is actually leading or may lead to some ways to store and reuse that energy without even generating hydrogen in the first place. With us to help understand all this is Dr. Tom Autrey, a lab fellow with the Pacific Northwest National Laboratory. So Tom, welcome and thank you very much for joining us today.
Thanks, James. Good to be here.
So first off, I'd like to start with that big picture that you outlined in the document you sent me so wonderfully. Why are we even talking about this? Why are we having this discussion about hydrogen to begin with?
There's a big interest in hydrogen, given its versatility, and I'll get into some of the specifics, but one particular example is there's a goal to decarbonize the grid in the U.S. by 2035. And when you talk to the experts, the modeling experts, they say that existing technology, batteries today, or batteries they expect by 2035, can do that up to 80, maybe even 85%. So that was great news. That made me happy. But they said that that's not enough. We need to get that last 15 to 20%. And we need novel approaches, novel ways to do that. Batteries just aren't going to be able to do 100%.
So, Tom, just to be clear, when we talk about the 85% and the 15% in terms of 2035 renewable energy, we're talking about we're talking about storing the energy in terms of making renewable energy, decarbonizing the grid by 2035. These percentages of what?
Percentage of how much of energy we can make renewable. So can we make the grid entirely renewable so we don't have to burn coal, to burn natural gas? And so to do that, we're going to need some storage options. So obviously, if you need energy, you use it, you don't store it. And so in the near term, as we build up all the renewable resources, we're just going to use them right away. But in the midterm and in the long term, when we overbuild, so that we can try and cover things.
So that we're at the point where we're creating more energy than we need at any given moment.
Exactly. And so the first thing is, as long as we can use the energy, let's use it. But when we have excess energy or when we're making energy and we don't need it, then we need to store it.
Mm-hmm.
So hydrogen is one way to do that, and that's the area we're focused on.
And one thing I want to point out for folks, because you mentioned them again in the wonderful information you sent me, was like many things related to renewable energy, it's sort of many answers to one question, right? It's wind, it's solar, it's on. And in terms of storage, it's the same thing. There's battery, there's potentially hydrogen. But in terms of the longer term, that 15% that batteries won't get us to or get us past, you mentioned a couple other potential technologies. Could you just kind of list the hydro, the
right.
Gravity? Give folks that list, because wanting to know that hydrogen exists in a realm of other solutions that also have their place, and then we'll talk more about why hydrogen is unique among them.
No, good point. There was a really good workshop a couple of years ago on where I learned a lot actually on long duration energy storage, and so experts from industry and universities and laboratories, and the batteries are certainly pretty well developed, and there's lots of great research going on in that area, but for long duration, that's where batteries struggle. So batteries are really good. People say 1 megawatt to 10 hours, battery will solve, and that could be 85 or 85%. It's related to that. But beyond that, if you need to store energy for a longer period of time or need larger amounts of energy, Then things like pumped hydro, solar, or pumped hydro behind a dam. So you could pump water up to a lake during the evening when no one's using electricity. And then during the day, when you need more of it, you let it back down again, and it turns a turbine, and you generate that. And that I really like that solution because it's pretty old technology, well known, but it's what I guess we like to talk about is it's not geographically agnostic, and so there are certain parts of the country you can do this in, and that's really leaves a lot of holes where you need some other solutions. Some of the other ones are solar thermal. So, maybe out in the desert somewhere where there's lots of sunlight, you can do solar thermal energy storage where you heat something up and use that heat, and then later on take the energy from that heat and get your energy back. There's gravity, where I've even seen where there's different approaches that I don't understand that as well, but they'll pick up a large weight, and then when there's excess energy, and then they'll let that weight slowly go down. It turns a motor or what, I'm not sure how that works. It's physics and engineering, and so that's also an interesting option for some places. But what we're interested in with hydrogen is it is geographically agnostic. The approach that we're looking at.
So I love that term, the geographically, in terms of hydrogen as it fits in those realm of different solutions, the geographically agnostic piece of it. And then you'd also mentioned the scalability, that it has a potential to be scalable in ways that aren't true of some of those more large scale fixed infrastructure projects that you just mentioned, that are also, as you said, very interesting. All right, so if now we've sort of, we've kind of laid out where does hydrogen fit in answering this long-term storage of energy generated by renewables, and kind of where does it sit amongst some of the other options available. I'd like now to turn to the work that you all are specifically doing, or colleagues of yours in the field are doing to help address some of the challenges and questions related to storing and transporting the hydrogen. And if you could, you hinted at it before with the chemical storing of it, but if you could give us a lead in before we get to your work, the ways of storing hydrogen now and transporting it, and some of the challenges related to that, and therefore why you're looking at the solutions you're looking at.
Yeah, the question about transport is really important. We're looking at applications where stationary storage and you don't have to move things, but there are things where you want to move it around. And currently the way that's done is either with compressed hydrogen gas. And so the Toyota Mirai is a great example. They're using special carbon fiber tanks to be able to hold pressures to 10,000 PSI, 700 bar. And so those are really high pressures. You need to have a really thick metal, but that's too heavy for a car. So for transport, you want something light. So they use carbon fibers. So that's a real challenge. But there's also liquid hydrogen, and that's really hard to beat because it's all hydrogen and it's a liquid. But and NASA does a great job with this. They have huge dewars where they can store hydrogen, but they're storing it at really low temperatures, 20 Kelvin. I don't know, it's like minus 250 degrees Celsius. I can't remember what that is in Fahrenheit.
It's
but
very,
really
very cold.
We're very, very cold, yes. Yeah. And so people are looking at dewars and doing that, but that's really expensive. You need to have a vacuum dewar. And then there's issues with what they call boil off. And so you lose hydrogen over time. And trying to keep it that cold, it's just, you can't keep it cold. It's the physics of that. And there are people trying to extend that life, but there's still challenges with that.
Yeah.
So
if we look at now the physical challenge of high pressure compression, and as you mentioned, the containers that involves, or the challenges of incredibly cold temperatures and maintaining those temperatures, you all are working on a third option, which is
our third option is looking at storing hydrogen in chemical bonds. We're chemists. We know we like to make carbon hydrogen bonds and break carbon hydrogen bonds, and so can we be creative in how we do that?
So to help me and some of the viewers understand this, Tom, I had one analogy I thought of, and I'm curious if you maybe have probably a far better one. But the idea being that hydrogen, and correct me if much of this is way off target, but hydrogen being a gas and being I'm going to call it sort of a squirrely gas that wants to get away before we can use it. And so the idea with chemical bonding it is, can we attach it to something else that wants it to sit in place and just kind of behave until we're ready to use it? Is that, you are looking for chemical solutions to grab onto this hydrogen, hold it in solution in a, as you said, at room temperature, ambient pressure kind of way, until we say, okay, now we need it again to create some energy. Is that, am I putting this in the right terms?
No, that's a good description, right? The hydrogen is, it's the most abundant element in the universe. It's not, it's usually bound to something else. And so when you can do electrolysis of water, with renewable to generate the hydrogen gas. And then the idea is, well, then how are we going to move that hydrogen gas? Do we fill up a bunch of balloons? Or, is there something, or do we have to cool it way down so that we can move it from point A to point B? So by binding it to a molecule, it helps to squeeze it down into a much smaller space that makes, you could transport it in a plastic container. So it simplifies that side of things.
Interesting. Oh, so the chemical bonding of it starts to solve the mass problem, or the space problem. It actually, as you said, it constricts it into a smaller space, but we're still talking about low pressure and regular temperature. But the chemical you're bonding it to is doing that work of saying, here's your hydrogen in an easy contained space. Is that
right? Exactly.
Yeah.
Exactly. And so what it does is, hydrogen, like you're saying, it's not, it's a swirling molecule, and when you try and press them together, it's really hard to compress, and that's why it requires high pressures. But you still don't get that much. But if you can add that hydrogen across the what we call an unsaturated bond, then that really gets it into a much smaller space.
interesting?
I'm trying to think of maybe some numbers off the top of my head. I think with liquid hydrogen, where you cool it, like I said, it's hard to beat. You can get 70 kilograms of hydrogen in a cubic meter. Okay. So, and then for compressed hydrogen, try with, I think 700 bar, I think it's around 30 grams in that you can compress into a space. It may not even be that high. I might be a little bit over. And it depends on what size tank if you use carbon fiber, you can keep it small. And like you pointed out, volume really matters when you're trying to move things. And then mass is, but you can't have something large. But then if I put this on a molecule, I can get it. I don't have to, have a heavy, thick tank. I can get about 50 grams, say between 20 to 50 grams of hydrogen in a cubic meter. Huh. So that I can store the hydrogen or transport the hydrogen.
So it starts to look potentially competitive with either the pressure or the really cool temperature versions.
It offers, I like to think, of another alternative. And
yeah.
So there may be times where you just say, let's keep it compressed and do it, or liquefy it. It's worth it. But there will be times when you say, well, we need an alternative to do this, to move it long distance or.
Sure.
So that,
Sure.
They're all, like I think you pointed out at the beginning, was really important, is there are a lot of solutions to renewable energy. There's going to be a lot of solutions to energy storage, and there's going to be a lot of solutions to how we store hydrogen. Now, there won't be one magic bullet, and it really will depend on, you have to think about the big picture. And so, really good questions.
Now, then we get to, what are you choosing to, as this, to form that chemical bond, to sort of grab onto the the hydrogen. My balloon analogy threw me off. To grab onto the hydrogen and hold on to it. And this is where I think we come squarely into sort of the green chemistry aspect of all this, which is an idea of, and you hinted at this already, of not causing additional problems environmentally, health-wise, whatever, while trying to solve another environmental or climate challenge. And
Right.
so, in other words, not using a chemical to store hydrogen that itself is hazardous or toxic or, causes problems that we don't want. That green chemistry perspective of let's solve this challenge while avoiding other environmental human health problems. In that regard, you hinted at this a little bit already, but as you look at the chemicals that can help you contain hydrogen, how is that concept playing out?
Yeah, no, excellent question. Again, there's no one magic bullet, but when you start to think about, so I mentioned have looked at ethanol. Other people are looking at toluene, and one of the molecules that has really piqued our interest more recently is what I like to call modified baking soda. So baking soda is sodium bicarbonate. And we're looking at potassium bicarbonate because it's more, in the long run you can get more hydrogen onto the potassium bicarbonate. And so potassium bicarbonate, the one way to get potassium bicarbonate is from CO2. And so if our whole goal is to reduce the amount of CO2 in the atmosphere, the icing on the cake would be, can we use that CO2 to store and transport energy? And so a lot of people are taking CO2, and the problem with that is when you want to convert it to something else, it requires a lot of energy. So we never try and fight Mother Nature. So what we're trying to do is just take what Mother Nature gives us, right? And so if we can take baking soda, potassium bicarbonate, we can add hydrogen to it using a catalyst, and we make a molecule called formate. And so what that does then is that's another, as you pointed out, a non-toxic chemical. So baking soda we know is pretty safe material. Formate is used as a road de-icer. And so what so we can remove CO2 from the atmosphere, use it to store energy. We're taking what Mother Nature gives us. If there happens to be a fire, it might be possible it's in an aqueous media, so it's stored in water. It's not going to start burning. It's not going to be flammable, and so that's so the flammability, the safety issues, the being around people. The downside is it doesn't store as much hydrogen. So it's kind of like, okay, well, how do we balance these things? And so that's kind of beyond the decisions that we're capable of making. But we can say, okay, here are all the positives. We can store 20 grams of hydrogen per liter or 20 kilograms per cubic meter. And so, but it's safe, and you can store a lot of it, and it's economical. And it's taking CO2 out of the atmosphere and using it to do something positive. And the goal is that you cycle it back and forth, so you can remove the hydrogen when you need it, and then when you have excess energy, you make hydrogen and you put it back on the molecule and store it for when you need it next.
Yeah, that's fascinating. And the baking soda component of it, again, to me, it's, as you said, there's clearly work to be done, answers to be found. But in that spirit of green and sustainable chemistry, of how do we store the hydrogen in a way that, again, it is, and what's interesting about what you're saying, not only not causing new problems, but actually helping to solve another problem by this element of carbon capture, the potassium bicarbonate, is that what, do I have that right?
So
Yeah,
potassium.
creating that, using that to grab onto the hydrogen for storage, and then recapturing as you need the hydrogen in storage. It's a at face value anyway, to me, a very elegant overall solution. I know a lot of work to be done, I'm sure, to get it where folks might want it, but such an interesting path to be following, I think.
I mean, and to be clear, we're not the only ones doing this. We're not
Sure.
the first ones to do this. And so there are a lot of good people working on this out there, and that's what we want. We all want to make safer ways to store energy and do this, where it's going to be affordable. And you point out, that one of the things we like to think about is, are there, can we hit two birds with one stone? Can we do, and so the other kind of angle to this that we got to in that paper was and it's a perspective, and so we're proposing ideas, and it definitely needs further research. Is the thing that really interested me about bicarbonate and formate was that it's maybe possible to directly reduce it electrochemically. So I apologize for if I'm getting too technical, but right now, what we use electrolyzers, solar power will generate electrons. We'll put those into electrolyzer. They'll split water and make hydrogen. And then there's this question of, okay, well, we have to do something with that hydrogen. Do we have our baking soda plant right next door? Or if we can't, then we have to do something with the hydrogen to move it. And so what we're really curious about is, can we capture CO2 from the atmosphere to make our baking soda mixture, and then just use electrons to reduce it and make formate? So we skip the hydrogen step, and we're making the same material. So people have asked us, can we ever make a hydrogen carrier without having to make hydrogen? And so this is, maybe it's one of the example where that can happen. And then, so at the end of the day, you say, okay, I have my formate. If I need hydrogen, I can release the hydrogen off and use it, and I didn't have to have an electrolyzer. And then another question we have is, well, can we just pull electrons back off again, and then get the electrons? So we're skipping hydrogen, and we're solving a long duration energy storage problem. So we have multiple options. And so what we would like to do, and we proposed others to help with this, is to look at the economics of this, to look at, okay, what would it take if I had to buy an electrolyzer and make hydrogen, and then if I couldn't have my baking soda plant next door to it, and I had to move the hydrogen, or could I use a different electrolyzer? And people are making these, and there's a lot more growing interest in reducing the bicarbonate to formate. And there are companies now that are looking at taking that formate and you can convert that to formic acid, which is another liquid organic hydrogen carrier. And then as a formic acid, that's 50 grams of hydrogen per liter. And then you can transport that. So it's a great way to transport hydrogen. So there's all these dimensions, which makes it really fun and rewarding to take a very simple molecule, as we talked about before, earth abundant metal, potassium, sodium. Can we use catalysts that are made from earth abundant materials, or do we have to use precious metals? A lot of the research starts with precious metals to understand, and then you can kind of go from there to come up with the cheaper forms of catalysts.
So there's a couple of things you mentioned there that I want to hit on, and then we should probably we can start to wrap up our conversation here. But again, I just, for myself and for anyone who was listening to that, to really put a circle around it, because it sounds so fascinating. The piece in that paper you mentioned, and folks watching this, we'll link to the paper. It was a paper in the Royal Society of Chemistry's Green Chemistry Journal that we'll link to. But is this idea that on one hand, you're talking about how can we link hydrogen to potassium bicarbonate as a mixture to store it, and then get the hydrogen back out to make formate, and then get hydrogen back out of that to use it again for electricity. And the second step past that in terms of efficiency, you're saying, I think, is why make hydrogen? Can we just go straight to making formate and then get hydrogen out on the backside to use it to create electricity? Right. That's step one. And then the next thing you were talking about are folks working on, well, why then have hydrogen as part of the picture at all? Let's just make the formate directly and get the electrons back out of the formate directly on the backside to regain our electrical power. Is that?
I mean, that's the question, right? Is what's the efficiencies of these processes? And so that's what our goal is to try and understand it. And to answer that question, do we, specifically for like a long duration energy storage, and one of the terms I like the modelers use is Dunkelflaute. And so it's a German term that means, the dark doldrums. So the sun's not shining, the wind's not blowing. So your solar panels and your wind turbines aren't generating electricity. You need stored backup energy. So do you store that as hydrogen, or do you store it as electrons? If you could store it as electrons and skip the hydrogen step, it's that has lots of potential complications, but it's high risk, high potential, high reward.
Yeah.
But again, back just one more, this versatility issue, right, is that we didn't get to touch upon much but hydrogen is a chemical reductant, right? And so having hydrogen, you can start talking about green steel manufacturing. And so there's a lot of people talking about, I think in Ohio now, proposing using hydrogen and for replacing coke and coal and reduction of iron ore to steel. So if you're going to need to store some of that hydrogen, you're going to have to release the hydrogen. So there's energy storage, but if we want, the ultimate goal is to reduce CO2 and carbon emissions, then hydrogen has multiple roles to play. And I think also with ammonia, which is another huge need right now, that's made by the hydrogen for that process is made by Haber-Bosch method, and you make a lot of carbon emissions. Could you do that with green chemistry? You make hydrogen, and then you may need to move it or store it, and then use that to reduce nitrogen to ammonia. So I don't want to put hydrogen out of business, but we do want to be honest, right? We want to ask ourselves all the time, can we, in any way we can make this more efficient? And so that's what we tried to touch upon in that perspective article.
And that last piece, so you're talking about, for most of this, we're talking about hydrogen and its role in producing power, or, grabbing electricity and releasing electricity. But in this case, you're talking about hydrogen's role in the economy to help supplant other carbon-based, fossil fuel-based components of other important industrial processes. Is that where hydrogen can play a role and help to reduce overall carbon emissions? Is that right?
Exactly. It's so the ultimate goal is to reduce carbon emissions, to get carbon neutral by 2050. We're going to need to store energy for Dunkelflaute. We're going to need geographically agnostic ways to move it around, and it's not only, it's versatile, so you can store energy. It's scalable. We can go from to Toyota Mirai up to seasonal backup storage. We're talking 100 gigawatt hours of energy storage, and it can also make a big role in reducing carbon emissions in industry. And iron, green steel is something that a lot of people are looking at now. And I think people have recognized, can we make ammonia from hydrogen? But our big question is, if you can't use that right away, can you take your two processes where you're making your hydrogen and use it right away? Then you'd use it. But it's always, if there's some way you have to move it from one place to another, then storing it is where we are putting it in the chemical bonds.
Yeah. It's a fascinating suite of work that's happening here, and all that I hope folks are following, and I suspect they are. The wonderful connections between the different parts of this research and seeing the potential of it. I know it, and folks, just so that's why I was really interested in talking to Tom, is to get a better view on, not easy challenges to solve, but a lot of incredible work being done at PNNL and other places to answer these questions, because on the backside is some pretty exciting and promising solutions potentially. Tom, we should wrap up here, but I want to ask you one other question, which is just on a more sort of personal and professional level. This is hard work, and I'm sure not every day of it is wonderful. but what gets you out? What gets you out of bed to do this work each day? What draws you to do this work?
Oh, that's a good question. You didn't warn me you were going to ask this. I'm stumbling over this. I love what I'm doing. You're right. Sometimes it's two steps forward, one step back. Sometimes it's one step forward, two steps back. But when it's solving puzzles and mysteries, and working at a lab, a national laboratory, is it's just a super rewarding. There's several thousand people here. If you have a question, there's someone who probably has an answer to it. And it takes work sometimes to track it down. And I've just had so much fun in trying to address this, the work with everything in chemistry, from chemical physicists to chemical engineers to systems analysis, We have all that, in our own backyard here to talk about. And if we don't have that, we have collaborators at the other laboratories and universities that and so it makes it, we know there's a pressing challenge. We know we need to come up with unique solutions. But it's solving a puzzle, I guess. That's what, maybe just, once it's frustrating. And then when it all comes together, it's extremely rewarding.
Wonderful. Any other closing thoughts that you'd want to mention before we say goodbye?
I think it's an all hands on deck. I don't want us to, sound like we're the only ones doing this. And it's, I've been very fortunate to have collaborators all across the US and around the world. And it's just really, it takes different optics. It's the diversity thing, right? I mean, it's not just a, physical organic chemist that's going to solve this problem. You need, computational chemists, you need material scientists, heterogeneous catalysis, electrocatalysis. So it's all of this that comes together and to try and solve something as challenging as we're trying to do here.
Absolutely. And folks, you can count on the fact that we're going to come back to Tom and his colleagues. And I hope many of the folks that he's referring around the world to take deeper dives on, because there's so much in this interview alone that you've highlighted that I would love folks and myself, honestly, to understand even more deeply, to see that potential. Because as I've had this thought in my mind that, we all know the phrase, the devil's in the details. When it comes to this kind of work and the green chemistry, the sustainable chemistry pieces of it, to me, that phrase becomes the angel is in the details. Because it's when we get into those details of the specifics is where the problems can start to get solved. And I love your idea that it's all these different people, all these different disciplines working around the world to try to put this puzzle together, essentially. And it's nice to know that it's happening, and it's also nice to see the work that's yet to be done and get a better understanding of it. So to that extent, Tom, thank you again very much for joining us, and best wishes with your work. And I hope we'll have a chance to talk to you again soon.
Thank you. No, I appreciate the interest, and it's exciting to talk about. It's been a pleasure.